सर एक बात कहूँ।
जी जी प्लीज।
सर मुझे आपकी स्पीड ज़्यादा लग रही है।
हाँ स्पीड ज्यादा है, लेकिन ये थोड़ा सा प्रिलिमिनरी था ये चीजें, तो इसलिए इन स्पीड पे मेरी थोड़ी ज्यादा है। ठीक है, सही कह रहे हैं, लेकिन आज 90 स्लाइड्स हैं तो मैंने कवर करने हैं, तो इस लिहाज से मैंने उस पर ही पेस्ट रखी हुई
अच्छा ठीक है सर।
है। तो अभी आप देखेंगे कुछ चीजें रहती हैं अभी भी, लेकिन आपको किस चीज की समझ नहीं आई? कुछ समझ आ रही है आपको कि नहीं?
नहीं सर, समझ तो आ रही है।
बेसिकली पहले दो लेक्चर्स तो आपके दे आर वेरी प्रिलिमिनरी लेक्चर्स, सो starting from lecture 3, then we will go into the design part using in the connections part of your course. तो फिर उस पे थोड़ा सा we will try to go steadily, but actually the course contents are so much that I have to cover them. That's why I go for 90 slides or 70 slides. By ideally I should go for 50 slides, and there should be 50 to 60 slides, but based on the content, so I have to go for more slides than 50. I'm sorry अगर आप लोग बोर हो जाते हो बीच में तो।
नहीं नहीं सर, बोर नहीं होते, समझ तो आती है लेक्चर की।
चले, थैंक यू। ओके, अभी मेरा गला बिल्कुल खुश्क है और रोजे की हालत में पता नहीं मैं क्या करूंगा अभी। चलें देखते हैं। Okay, we are going to start now. We finished discussing the earthquake loading and the wind loading part. Now we will have some introduction to mean return period. Okay. Now the definition of mean return period is it is the average time period which is based on geological and historical records. Okay, in which there is a good statistical probability that an earthquake of certain magnitude or a hurricane will recur is called mean return period. Okay, mean return period means the recurrence of any significant earthquake, okay, during the lifetime of your structure. And you know that you design your building for the life of your building is 50 years, and you start constructing your building in 2021, and if you add 50 years into the 2021, so it will come out to be 2071. So how can you make a futuristic estimate that in the future 50 years this will be the magnitude, or this earthquake will recur, or this wind speed will recur? So basically for this, in order to derive this information, you use historical records, and make use of probability. Okay, now you will see that what is a recurrence interval. Recurrence interval is the time period. Okay, a time period in which a significant earthquake recurs, or a hurricane or storm recurs. So this is called recurrence interval, and obviously it is in terms of years. Okay, what is the probability of accidents of an event in 1 year? Like this is an inverse of this recurrence interval. Okay, if you take the inverse of this recurrence period, so you will get the probability of accidents in 1 year for that event. So this we call probability of accidents. And how probability of accidents and return periods are formulated or related? They are formulated through this formulation. Okay, now this P represents the probability of accidents, and represents the years. Okay, one R means mean recurrence interval, or the mean return period. This is the return period. Okay, and basically for winds and for earthquakes, we design our structure, or we design our buildings for certain intensity of the wind speed or the ground motion, which has some specified return period or specified probability of accidents. Okay, this is probability of accidents. Okay, Now we know that probability of accidents as per the IBC code for wind speed is 7%. If you use 50, you use n as 50, you use the value as 7%. 7% means this one, and you use this formulation and you calculate the return period of such an event. So it will come out to be, R will come out to be 19 years. So probability of 7% in 50 years correspond to a recurrence or return period of 19 years. So in order to convert from the exceedance probability to return period and vice versa, you can use this formulation. And we use this formulation for wind loading, okay, wind loading, wind load, and for earthquake load, okay, earthquake load. Okay, now this isn't just an example, like a structure is expected to have a life of 50 years, okay? So this is 50 years life of, this is the life of your structure. And the where this building is constructed, over there the mean recurrence interval of a windstorm is 95 years. And what is the magnitude of wind? 150 miles per hour. So what we want to know, we want to know the probability of accidents, chance of occurrence of this intensity, okay, in 50 years. So we will use simply this formulation. You plug in the n value is 50, R value is 95 years. So basically you can use, this is the formulation, 1 minus 1 by R into N, okay? So 90%, 95% return period means in 50 years, 41% chance of accidents of this much storm, like this velocity. So there is a 41% chance that structure will be exposed to windstorm exceeding a wind velocity 150 miles per hour. So this, the same formulation you can use for the earthquake, okay? Now there is a ground motion which has a probability of accidents like 95% is the probability of 95% is the return period of a ground motion which has an intensity of 0.4 G. So you can convert from the return period to probability of accidents, okay? Similarly, we can convert from the return period to probability of accidents. So according to UBC, the loading, or as I told you that there were different seismic zones we have discussed. We discussed zone 1, we discussed zone 2A, 2B, 3 and 4. So these zones are corresponding, or they are referring to PGA with a return period of 475 years. Or you can term that the ground motion corresponding to 10% chance of accidents in 50 years. So this is according to UBC 97. So basically idea is to give you the information that how you can convert and how probability of accidents and mean return periods are interrelated, okay? These are just demonstration examples. For example, you want to calculate or you want to include the impact loading effects into your load. What you are going to do, how do you incorporate impact loading? You just increase the live load by 25%, okay? This is about impact loading, how you can consider the impact loading effect into your loads, okay? Now, so now next up is the factors for LRFT and AST and the load combinations, okay? This is some of the rough work, okay, which we have done in the last class, so they are there. we already finished discussing that ASC E7, which is the loading code which is being referred by IBC, they require you to design your building for such a wind speeds which has a probability of accidents of 7% in 50 years. If you want to calculate the return period, it comes out to be 19 years. Okay. Okay. Now, first up is the load factors and the resistance factors for LRFD. Okay. Now, this, if you see this formulation, so this represents RU value. Or if we go to the initial slide, this is the factored loads. We call that factored loads. Okay. Factored loads. Okay. So this is the strength or the resistance. And we have discussed that Rn means nominal resistance. If we multiply the resistance factor with Rn, we call this as a whole as design strength. Okay, design strength. Okay, this is in LRFD. So the basic is that you should have the RU value which is derived from the factor load. It should be always equal or less than the design strength. Okay, means that the design strength should be more than the required strength, and this RU we call the required strength, and this is the sum of the load effects. Okay, are you following me? आप लोगों को समझ आ रही है?
Yes, sir. So far, so good.
Actually, I'm very tired. I don't know how I will be able to continue. I can barely speak. I don't know. Let's hope I can make it. So the next step is the load combinations. Okay, I will try to conserve my energy. Okay, now in order to loads or load combinations which we will use in the design or analysis of our members, the AISC, which is the American Institute of Steel Construction specification, it section B2 requires you to load factors. Okay, and these load factors they have derived from this loading code, which is American Society for Civil Engineering. Okay, now these load factors and load combination are based on statistical studies. Okay, now the 7 combinations are follows. If you have this type of loads, dead loads, earthquake loads, load due to fluids, live loads, snow loads, or rain loads. So for these type of loads, these load combinations are prescribed by AISC, and AISC takes it from ASCE document. So these are the load combinations. 1.4 dead, 1.F means the load due to the fluids. Okay, but in the when we talk about the steel structure design, so we usually omit the fluid pressure, we omit the earth pressure, we omit the self-retaining sustaining force. So these are omitted, and our load combinations are reduced, or they have been modified. Okay. So if you look at these load combinations, so let's for example look at this one. So we have discussed that the load factors in LRFD are always greater than 1. But over here you will see that there is the load factor which is less than 1, but they are combined with wind and earthquake. This is so because we know that the wind and the earthquake try to they are the lateral loads. The wind and the earthquake. Okay, earthquake, they are the lateral loads. Okay, they are the lateral loads. Okay, and they try to destabilize your structure. destabilize structure, but the dead load, it tries to stabilize the structure. Okay, so in order to enhance the effect of the wind and the earthquake load, the dead load factor is reduced. Okay, so this is discussed in the theory as well. Okay, you can go through it. So wind and earthquake load may tend to overturn the structure, but the dead load will have stabilizing effect. That's why the dead load is reduced in this combination in order to have more effect from earthquake and wind. Okay. Now, when we look at these load combinations, so you will see that there are different loads which are acting on the structure at different instants during the lifetime of your building. So one of the loads will always represent the dominance. Dominance means the maximum in the life of the building. The other factors, the other loads in any load combinations, they represents the any arbitrary value during the life of the structure. Okay, so when you look at these load combination, one load will represent the maximum value during the life of the structure, and the other will represent the any value during the lifetime of the structure. So in this way, these load combinations have been formulated. Okay. So we talked about LRFD. We talked about okay, it's not working. Why? LRFD. In LRFD, we use resistance factors. Okay. And these factors are less than 1. Okay. Now, for the as and we already discussed that in LRFD, when the factor loads are applied to the structures, they reach certain limit states. So you will see that yielding is a limit state, compression, buckling. So for these kind of limit states in LRFD, the resistance factor is used to be 0.9. So you reduce your resistance by 10%. Okay. And for rupture case, you reduce your strength by 0.25%. Okay. So the rupture or fracture is a brittle failure. So so the yielding is compression or buckling is somewhat the ductile failure. So we do not reduce our material strength by that much of amount. And for the rupture case, which is a very certain, so we want to be on the safer side. So we reduce it by more than what we reduce it for the yielding, compression, and buckling limit states. Okay. Now, when we look at the safety factors for allowable stress or allowable strength design, so you will see that we discussed that the required strength should be less than the allowable strength, and Rn value is the nominal strength, and you will see this notation. This notation represents the factor of safety. Okay. When you divide the theoretical strength by the factor of safety, so this is called the allowable strength. Okay, this as a whole is called allowable strength. This Rn is called the required strength. Okay, and the basic equation is that the required strength, which comes out from the effects of the surface loads. Okay, we add surface loads. Okay, to get the required strength. Okay, this is the effect of these service load addition. So these are the now when we look so okay, the load combinations in ASD, they do not use any load factors. Okay, they just the one value, the unity value in ASD represents the maximum value. Okay, but in some load combinations you will see that they are reduced. These are not the load factors actually. Okay, they are just representing that in this case there is a very less chance that the dead load and live load or the roof live load should be acting together. Okay, so this is one of the combination. Okay, this is just not the load factor. This is not a load factor. Okay. So you can have a discussion on this. So this is briefly discussed. What I have tried to explain to you on this slide. Okay, now we said that we are going to use two philosophies, which are LRFD, and we will also use the AST for the design and analysis of our members. For LRFD, we have seen the phi value or material resistance reduction factor for yielding. We have seen it for rupture. For AST, we use factor of safeties, and these factor of safeties will be 1.67 for the same limit states. Okay, and we will use 2 factor 2.0 for rupture limit state. Okay, we will divide our nominal strengths by these 1.67, and for this limit state we will divide our nominal strength by 2. In case of LRFD, we will multiply by 0.9. Okay, this happens to be 0.9, and this phi is 0.75 for the rupture case in LRFD. Okay, there is an example. Okay, this is an example. Okay, this is very simple example. You can refer to the Sigwai book, chapter number 2. It is the same 2.1 example. Okay, now a column in the upper story of the building is subjected to certain loads. Okay, what are those loads? These are those loads. Okay, dead load 1.07, 96, 46 is the floor live load. So what it is asking you to determine the controlling load combinations. Now what you have to do for these all type of loads, you have to come up with all combinations which are mentioned in the code. Okay, and by code I mean IBC, or I mean ASCE. Okay, you can refer to the specification as well. So it will give you certain number of combinations for these loads types. Okay, snow, roof, floor, dead. So it is asking you to determine the load combination for LRFD, and it is asking you to determine the corresponding factor load, and the corresponding factor load corresponds to RU, required strength. Okay, then if the resistance factor is 0.9, what is the nominal strength? So we know that our nominal strength is R9. Okay, Rn, sorry. So how it has proceeded. So you can go through the theory and you will see that there are 6 combinations for these loads which are mentioned by the code. Okay, so you have to check each and every code, every combination. Okay, and you have to see that which combination is giving you the maximum value. Okay, so the combination number 2 is the controlling combination, and this is answer to the first question. Okay, now we know that this RU in LRFD should be LRFD, should be less or equal to this one. We have this value. This is coming from here. Okay, so you can calculate, we have been given a phi value. This is 0.9. so if you use this phi value, so you will calculate the nominal strength. Okay, now if I go back to this example again, so now it is asking the same thing in case of AST. Okay, this was in the case of LRFD. This is in the case of AST. So if you go through this slide, so it will, now you have to refer to the code. It will give you certain combinations. Okay, now you have to see which combination is giving you the maximum value, and this maximum value will be your allowable strength. sorry, required strength. Okay, this will be required strength. Okay, so now you have to use this formulation. We know that in case of ASD, this required strength should be less than or equal to this allowable strength, and we know the factor of safety in case of yielding. Okay, you can use this factor of safety. This will go to this side, and similarly you will calculate the nominal strength. So you have calculated the nominal strength using both LRFD and ASD. Okay, the controlling load combination for LRFD may not control the ASD. It means that you will see that this is combining, this is dead load, live load is controlling. And let's see in case of this is also controlling, the same combination is controlling, I think, dead load, live load, and S. Let's see. Dead load, live load, and S. The same is controlling. Okay. Now, now we have seen that in ASD and in LRFD, they use the load factors. Okay, load factors are used in LRFDs. Okay, and resistance factors are used. Okay, factors. Okay, so this be represented by gamma, and this be represented by phi. Okay, and in ASD, so this is LRFD. Okay, for ASD, what we have that we use this values, factor of safety. So how these two are related, or how these three are related? So we will make a comparison between LRFD and ASD for a case of tension member. When we make this comparison, we come out with this relationship between factor of safety from ASD, and this, it comes out from the LRFD. This is the relationship between factor of safety and resistance factor from LRFD. Okay, and how do we proceed with the derivation? So you can go for this, you will start with this one. So we know that this is, I think, R and nominal strength. You can calculate the nominal strength in LRFD, you calculate the nominal strength in ASD. So basically you equate them together. Okay, so you put the value of RU, okay, for a case of dead load and live load only. Okay, so what you will get at the end, that the safety factor of safety of ASD case and resistance factor in the case of LRFD, they are interrelated with this through this equation. And this equation is valid if the live load is 3 times of dead loads. Okay, you have dead load, you have live load. Okay, this is for the case of dead plus live load only. So if the live load is 3 times of dead loads, live load, let me see, this is live load. So this relationship will hold, and this relationship will hold for the case of tension member. For a case of compression member or for a case of flexure member, this will not hold. Okay. Oh, if we make a comparison, okay, and if we go for the dead and live case only, we use the load factors 1.2 dead, 1.6 live, and we equate it with this design strength. And for the case of yielding, this is say 0.9. So this equation will be get modified. Similarly, you carry out the same operation in case of the ASD, and if you divide these equations, okay, these equations, so this will be reduced to this, and this we have evaluated this case for the dead load and the live load only. You can do same for this dead load case only. So if you do the same operation, So you divide the LRFD equation and you divide by the ASD equation. So what will happen? You will plot this value, okay? So when you plot this value, like it's saying that equation 1.96, this one, and equation are shown plotted in figure 1.191. This is that figure 1.19, okay? So the design of tension members will be the same in both LRFD and ASD for the case of live load and dead load ratio is 3. What it is stating that if we consider a tension member which is subjected to live load and dead load, and if the live load is equal to 3 times of dead load, the design made by LRFD and ASD will give you the same cross section, same design, same cross section, okay? Same cross section, same design, similar design, you can say. And this is evident by looking at this graph. So you will see that LRFD divided by ASD. What is this representing? This is representing this equation, okay? This, okay? This is reduced to this form, okay? And on x-axis, this is the ratio between the live load and the dead load, okay? When the live load is 3 dead and the dead load is 3. So if we take a ratio of live load to dead load, it comes out to be 3. So when we have this particular case, so it says that the ratio of LRFD and ASD for the case of dead and live load will be the same. Like the design carried out by the LRFD, and ASD will be the same, will be similar, okay? Okay, now if the live load and dead load ratio is 2, if you project this line here, it will intersect somewhere here. So what will happen that if the ASD will result in a larger cross section as compared to the LRFD, okay? When the live load and the dead load ratio is less than 3, so the ASD will be conservative. If the live load and dead load ratio LRFD will be conservative, but this will be not, will be about 3%. Okay, for explanation, you can go refer to this one. As the live load to dead load ratio becomes low, that is, dead load becomes more prominent, there will be economy, okay? Economy using LRFD. Like it is saying that if this ratio is less than 3, so the cross section or the member you designing with LRFD will be economical as compared to designing with ASD. If this ratio is equal to 1, so LRFD and ASD will give you similar economy, okay? So what else it's saying that with life to death ratio larger than 3, ASD will slightly give you more economy than LRFD, but this is not that much, it is about 3%, okay? So this is demonstrated here, 3%, this is one. So in this range, LRFD, ASD will be economical. And I mean this range, okay? This range. And in this range, LRFD will be economical. Okay, this is valid for this dead and live case only, okay? If you evaluate the same thing for 1.4 debt, so you get no relationship. Okay, you get this kind of information. Okay. So the next is that why we should use LRFD. So there are some merits of LRFD, why we should go for LRFD, not the ASD. So you can go through these certain points. So I will end my lecture here. So you can go through these merits of LRFD by yourself. Okay. Okay. Let's come back to you. Again. Now, any questions? आप लोगों को समझ नहीं आई तो आप पूछें, आपके पास टाइम है. आप लोगों को समझ आई? Did you follow what I have shown you in the last part of this lecture? What we have discussed?
Yes, we will review so far so good, sir.
Okay, it's good for in your case. Sir, if we want to take temperature loading in the what should be the factor? Okay, I have to check that what is the factor of safety in the case of ASD for temperature loading. I have to see that. Okay, I cannot remember it. Right now, what we will do, we will design for tension, compression, buckling. So that was included in your lecture, but I will check it. I will surely check it. Okay, what is the factor of safety in LRFT for temperature loading? Okay. Now, one thing is that this factor of safety is against some limit state. It is not against dead load or temperature load. It against buckling. It is against yielding. It is against fracture. It
So
is
slide
against.
68 per sir.
Let me go there. 68. Let me see. Yeah. Yes. Load factor. You are talking about load factor. Which one?
सर इधर 0.5 लाइव लोड क्यों किया हुआ है सर?
देखें
सर लाइव लोड को ज्यादा नहीं करना चाहिए सर.
देखिए, मैंने आपको बताया है कि लाइव लोड एक कॉम्बिनेशन में इट विल बी द मैक्सिमम. दिस विल नॉट बी मैक्सिमम इन एवरी कॉम्बिनेशन. These combinations are derived from real data. Like a building, if you have live load, if you dead load, what will be the different proportions of these loadings? So these are the loadings combinations which have been derived through statistical analysis of some real data. And at the end, they have come up with these combinations. So you cannot question it. Okay, I can question it, but we have to go back to its essence of why this is there. But for the time being, what I can tell you about it, that they have been derived from statistical analysis. They were not this, that okay, let's make 1.2, let's make 1.5. No, they have used probability theories like reliability theory to derive these load coefficients or load factors. And this statistical analysis is always performed on real data. This is not a very this was not performed on arbitrary data. So there was some original data, experimental data, and they have used the reliability theory to derive these load coefficients, and that's why they have put that into the code. And obviously they have tried to make to the safer side, like for example, if the load factor is 1.2, maybe they have shifted it to 1.6. Maybe you have seen in statistical analysis there is a one standard deviation and mean, and one plus standard deviation, one minus standard deviation. So this kind of stuff has been used to come up with these factors. This is what I can tell you, but I can go into the detail again, and I can get back to you if you are not satisfied. जी Did you get the answer of your question?
क्लियर है सर।
ये देखें स्टेटिस्टिकल एनालिसिस से ये कोफिशिएंट्स आए हैं लोग, ये कोई इस तरह आराम से बैठ के उन्होंने नहीं किए, ठीक है। बट आई विल श्योरली लुक मोर फॉर द मटेरियल, आई कैन कम बैक, maybe we can discuss it in the coming class as well, okay?
Okay sir.
अच्छा, आप लोगों को नींद आई है कि नहीं इस लेक्चर में?
थोड़ी बहुत सर।
थोड़ी बहुत? एक सेकेंड, अच्छा थोड़ी बहुत नहीं, वैसे नींद